Particles and waves, diffraction. Finally, light was deemed a wave when it showed interference effects after diffraction. Let's take a close look at diffraction. Here we have, in this situation here, a barrier, and we're looking down on these wave fronts heading towards the barrier. Imagine yourself just hanging from a hot air balloon looking down onto the beach, and here are the plane waves heading towards the barrier. As you can see, once you reach the barrier, some will be reflected off, but some will pass round the barrier, and it's this bending of the waves which we call diffraction. If we use shorter wavelengths, you can see that the phenomena called diffraction is not that good. Short wavelength waves don't diffract as much as long wavelength waves. Now here's a picture from the PHET simulation site, and you can see what happens when we pass plane waves through a gap. We can see in this situation here that waves pass through, they tend to bend slightly like that as they pass through the gap. If we make the gap smaller, those waves which are diffracted tend to become more circular, until you get to a stage where you make the little gap almost as small as the wavelength, or even smaller still, and the plane waves become circular waves. And this is a consequence of a famous theory called Huygens theory, but we can see in action live here. Light waves will show diffraction if the gaps are smaller than the wavelengths of light. And here's a situation we have two slits, and we have another effect taking place. You can see the first diagram on the left here. We have two gaps in the barriers, and the plane waves pass through these two gaps and create circular waves. They're diffracted. But the two sets of diffracted waves start to interfere with each other. And as one crest reaches one crest, they will add together in what we call constructive interference to produce a bigger wave. And you can see a little graph here of the the irradiance or the intensity of the light at each particular point where the waves have got constructive interference. Now, if you make the distance between the gaps smaller, you can see that we don't get as much areas of constructive interference. In fact, if we make the gaps very close together, you can see that all the areas of the interference pattern is all smudged into one. So diffraction of plane waves happen when they pass through two gaps. The circular waves then interfere and create places of constructive and destructive interference at certain positions. Note that when the two gaps are brought closer together, the amount of maximum and minima decrease. And note also that the irradiance is more concentrated at the centre maximum. In 1779, Thomas Young experimented with light to see if light could produce an interference pattern. If it did produce an interference pattern, then we could say that light was a form of waves, just the same way as water waves interfere and also sound waves interfere. If we could show light interfering, showing the bright, dull bands as we saw in the sound waves, then light would be a waveform. So in 1779, Thomas set about his experiment starting with a light source. He put a red filter in front of it to make it the one colour monochromatic light. And then what he did was he put a single slit in front of the lamp, and this was to make the light coherent. Remember, we did the experiment with the sound waves. We had to have the two speakers coming from the same signal generator. So it's the same with light. To produce, or to even attempt to produce an interference pattern, you must have the light coming from a coherent source. And in order to do that, we had to narrow down the lamp's filament into a tiny little slit so that the light coming out of the slit here would be coherent. And we'll talk about the coherence of light a little bit later on. So the light then was coherent and it passed through the double slit. And of course, when light passed through the double slit, you had a diffraction effect taking place, and the diffracting circular waves of light should interfere to produce dark, bright images on the screen. And this is exactly what Thomas Young found out. He found out that on the screen you had a kind of smudge of red, and then kind of like, if you look close enough, you had other little smudges of red interspersed with the darkness where there was no light. So there was a big smudge of light, no light, another smudge of light, no light, another smudge of light. And this proved conclusively that light did undergo interference, and therefore light was belonging to a waveform, because after all you could reflect light, think of a mirror, and that added to the wave nature of light as well. So we had interference, we had diffraction, we had reflection, so it seemed to be, because of Young's experiment, his famous double slit experiment, light was a waveform. Just a wee word about coherent and incoherent light. In order for interference effects to be seen, the light source must be producing light waves which are coherent. So what do we mean by coherent? Coherent light has got the same wavelength and same frequency. Coherent waves have got the same constant phase difference. Now that's quite hard to understand, and it only can be helped by looking at these two pictures here. You can see in the top picture we have the hands of a clock going round, the blue and the red hand, and there's a constant phase difference between them. We say they're in phase. Why is there a constant phase difference? Because the blue hand leading the red hand always keeps the same distance ahead, as you can see in that diagram there. So they're what we call in phase. So you'd mean that the peak of the wave and the peak of the other wave must be the same sort of kind of distance apart as they travel along. The picture below shows two clock hands which are completely out of phase. You can see that the blue hand is catching up with the red hand, and therefore the phase difference, the difference between them, is actually increasing and decreasing as it goes around that circle. That would be two waves where the peaks of one wave and the peaks of the other wave are constantly crossing over each other. So that's what we mean by a phase difference. So in order to have coherent light, you must have a constant phase difference, and that's like the top picture. And also the waves must be travelling in the same direction, and they must be travelling with the same speed. Now this all can be summed up with looking at two types of human activity. Think first of all of a coherent band marching down the street, everyone in step, everyone doing the same thing, keeping the same distance apart, going at the same speed and going in the same direction. That's what we'd call a coherent band. And imagine another human activity of a crowd leaving a football park. You would have everyone leaving in different directions. They would all be moving at different speeds, and they'd all be doing different things with their arms, whether they won or lost, and therefore they wouldn't be a coherent source of people walking. So that's the kind of light we must have to have interference effects, coherent light. And that's why Thomas Young put that little slit in front of his lamp, so that he could cut out nearly all of the light from the lamp except a small part of it, and the light coming from that small part was coherent and travelling in the same direction. Two light sources which we'll be dealing with, where you can see incoherent light comes from a light bulb, and that's why you have to narrow down a gap on that little filament there so that the waves coming off it will go in one direction. If you use the whole filament without that gap that Thomas Young used, the waves will be coming off at all different angles and all different directions and different frequencies. But a laser light is coherent, which means you're going to get one colour travelling at the same speed, but all the waves are travelling in the same direction, same wavelength, same frequency, and have all got a coherent light. So that's the kind of light we need in order to produce interference. Now, Thomas Young didn't have the luxury of having a laser beam to do his interference pattern experiments. We do, and that's why we don't need to have a single slit in front of the laser, because the laser light is coherent already. But here we have a situation where we pass the laser light through two narrow gaps, and it produces an interference pattern on the other side. And you can see from the graph that the interference pattern consists of red and black lines if we use a red coloured laser. But you can see also that the interference patterns kind of spread out a wee bit, it's kind of smudged out a wee bit. Now if we pass the same laser beam through a piece of plastic with four slits in it, four narrow gaps in it, then what happens to the interference pattern is it becomes much sharper, it becomes much clearer, and we can easily distinguish more of the interference pattern on the other side. The interference pattern becomes much sharper compared to two lines. So what we have to do now then is pass the laser beam through what we call many slits, and the many slits, the many gaps, can be provided by using what we call a diffraction grating, and that's what we'll look at next. But first, a little bit of the theory. So here's an explanation why we get these bright spots on a distant screen, these interference patterns. Now, if we concentrate on the central maximum, that's the first central bright spot there, we can describe that in terms of these diagrams. Now, these diagrams are mocked up diagrams. They're not true to size. Remember, we're dealing with very, very small wavelengths, very, very small gaps in the diffraction grating. In this case, we only get 2 gaps in this diffraction grating. Now, the reason why we get a bright central point is that the waves from this one arrive here and the waves from this one arrive here, and there is no path difference. So when the waves arrive, the peak of one wave from the first slit and the peak of the other wave from the second slit arrive in phase, which means peak meets peak, trough meets trough, so you get constructive interference. So you get a bright spot at the central maximum. And that's why it's called the central maximum, because it's the brightest part in the centre of these displays. And you can see you're going to have another maximum here, another maximum here, and likewise on the other side, another maximum, another maximum. But the central maximum is a special one because the path difference between the slit and the screen is exactly the same, which means the waves arrive in phase from each of the slits. Now remember, that diagram is a sort of kind of exaggerated diagram of what's happening to let you understand what's happening when the waves arrive at this particular point. So what happens when we get the first maximum? Well, the first maximum occur only if the crest meets the crest and the trough meets the trough. And you can see that this will only happen because we have got the waves coming from the top slit travel towards the first maximum position on the screen, and the waves from the bottom travel a little bit longer. Now that distance is very important. That's called the path difference. And if that path difference is equal to exactly one wavelength, then you can see that when we get to the top of the screen, we have all the waves in phase. The waves from the top slit and the waves from the bottom slit are going to arrive in phase. Crest meeting crest, trough meeting trough, and therefore you're going to get constructive interference again. You're going to get a bright spot here. So that condition for the first maximum is that the path difference at that particular angle has got to be one full wavelength. And likewise, we get to this one up here. This is the second maximum, and you can guess what the path difference is going to be. It must be one full wavelength more in order for the crest to match up with the crest from the second slit. They must have a full, there must be a wavelength of a difference. So therefore, the path difference for the second maximum must be 2 wavelengths. But we'll look at that theory a wee bit later. In fact, on a diffraction grating, we have many of those little slits separated by a certain distance d. And d could be the number of lines per millimetre scored onto these diffraction gratings. That's like a line, that's like a line, and you get a tiny, tiny little gap in between them. And that's where the light passes through. Now, this is what we call a diffraction grating, because you can see that we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 lines. So we can work out the distance between those 10 lines. So why do we use a diffraction grating with lots of lines scored on it? Well, because as we saw earlier, when you have more little slits, you're going to have a much sharper interference pattern on the screen. And that's because all these waves are all travelling towards it rather than just 2 waves. It's going to be brighter and it's going to become much sharper, which is going to be easy for us to measure. Now here's a real diffraction grating. You can see the microscope image of a diffraction grating here, and you can see the little sort of like lines in between and the little gaps, which are these black marks here. And that's the black marks are what the light passes through. These are the kind of dark marks. And you can see that over the course of about 1.1 of a millimetre, you're going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, about 11 of these spaces. So what we can do is, rather than describe the diffraction grating like that, we usually describe it as this up here, 100 lines per millimetre. That just really means there's going to be 100 spaces per 1 millimetre. This one here has got even a smaller gap because there's going to be 300 spaces, or lines as they call them, per millimetre. And this one here's got 600 of these little spaces here over the course of 1 millimetre. So you can see how small the distance between each of the slits are in a diffraction grating. Here we have one here with 500 lines per millimetre, and that's what we call a linear diffraction grating, very much the same as these ones up here. But the most important thing to notice is, what does the 500 lines per millimetre mean? It means that 500 little spaces between the gaps cover a distance of 1 millimetre. Now, how do we actually find the distance d between the slit spaces? Well, here's a kind of representation of that previous one. You can see that over the course of 1 millimetre, we have got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We've got 10 lines. So to find the distance d, which is really the distance or the length of the line, distance of the line between the slits, we just do the following little formula. We say the distance d must be equal to the actual length, which it's covered, divided by how many lines are there. In this case, we've got 10 lines covering 1 millimetre, so d must be 1 millimetre divided by 10. That comes out to be 0.1 millimetre. So 0.1 millimetre, convert it into metres, because that's the standard measurement, gives you that this little distance between the slits here is going to be 1 times 10 to the minus 4 of a metre. Now, here's the beginning of what we call the diffraction grating. There's a simple diffraction grating here with just 2 slits on it. We're going to analyse 2 slits rather than a full lot of them, and we're going to come up with a formula which will predict where the interference pattern will be. So that distance between the slits is distance d, as we talked about earlier, and you can see that the rays of light from the bottom and from the top slit go off at an angle of theta. Now, what we can do is we can concentrate on what we call the mth part of the interference pattern, the mth bright spot. We could say it's the first bright spot, but in this case we'll call it the mth bright spot. Now, for that to happen, the path difference, this path difference in here between the top waves and the bottom waves, must be a whole number of wavelengths, must be m wavelengths. So if we take that little triangle out here, that's really a right angle triangle, and draw it over here, we can see a better description of what's happening. The distance here, the triangle, is the distance between the slits d. That angle there, theta, is exactly equal to that angle there, theta, with a little bit of geometry. And this distance here becomes the path difference there. So we can say that sine theta is equal to the opposite divided by the hypotenuse. So sine theta equals p divided by d, the path difference divided by the distance between the slits. Now we can rearrange that to have p equals d sine theta, and p is becoming the path difference. So what's the condition for a maximum of constructive interference? The path difference must be a whole number of wavelengths, and that whole number of wavelengths is represented by m. So m lambda is a condition that's going to give you constructive interference at that angle which we look at on the screen. So m lambda equals d sine theta, and that's what we call the diffraction equation. So for example, if I was looking for at the first maximum, the equation would become 1 lambda equals d sine theta. If I was looking for the second maximum, the condition would become 2 lambda equals to d sine theta. So it's a very simple formula to actually work out. So here we are again. This is the summary of the equation. There is the diffraction grating drawn in simple form. That's very much a kind of made up diagram. But here's the actual sort of interference patterns that we get. There's the central maximum across from the central. We know that the path difference to get to the central maximum must be 0. And there's our diffraction equation. M lambda equals d sine theta. M is what we call the order of the maximum. Lambda is the wavelength, obviously. D is the spacing between the diffraction slits, which we saw earlier. And theta is the angle in which the ray of light passes up towards the interference pattern. So if we were looking at the second maximum, our equation would be 2 lambda equals d sine theta, where theta would be the angle towards the second maximum. Remember, this diagram here is drawn very much larger than what it really is. So here's an example how we can use the diffraction equation to find the angle from the central maximum. Here we have our laser which passes through the diffraction grating. There's the central maximum, which is called the zero order interference pattern, and you can see when we count we've got the first order and we've got the second order. So we're looking at the second order interference pattern. Remember, the laser doesn't need another slit in front of it because the laser light is coherent. So what we asked to find here, find the angle from the central maximum, that's that angle in here from the central maximum, to the second maximum when a laser of wavelength 650 nanometers is shone through a diffraction grating of 30 lines per millimeter. Okay, so what do we do here then? Well, we start off by using the diffraction grating equation, which is a well-known equation. It is m lambda equals d sine theta. We can rearrange that equation to find out what sine theta is, because after all we're looking for that angle. And therefore we get sine theta equals the m times lambda divided by d. Now before we start putting all our data in, I'd like to find d, which is the slit spacing. And to do that we know we're going to deal with 300 lines per millimeter. So to find d, it's really the length divided by the number of lines covering that length. So over the course of 1 millimeter, we've got 300 lines. So to find d is going to be 1 millimeter divided by 300, which is going to give us an answer of 3.33 times 10 to minus 3 millimeters. That's the little slit spacing on the diffraction grating. Now, I don't want it in millimeters, I want it in meters. So I've got to divide by 1000 again, which is the same as multiplying by 1 times 10 to minus 3, which is going to give us the distance in meters between the little slits of the diffraction grating, and that's going to be 3.33 times 10 to minus 6 meters. Now, I'm quite happy I can go and fill in all the rest of my data. And that's it there. Now, because I'm looking at the second maximum, m must be equal to 2. The wavelength is 650 nanometers. That means 650 times 10 to minus 9 of a meter. Theta is the angle I'm looking for, and I've already worked out the slit spacing d. So I put everything into the equation and I get sine theta should be equal to 2 times the wavelength 650 times 10 to minus 9 divided by 3.3 times 10 to the power minus 6. That gives me that sine theta equals 0.39. I can find the inverse of sine theta, and I now know that the angle theta is 23 degrees. So the angle from the central maximum out to the second maximum is an angle of 23 degrees. Here we can use the diffraction grating equation to find the wavelength of laser light. It says determine the wavelength of a laser light when the first order maximum is found to be 15 degrees away from the central maximum, and the diffraction grating we're using has 600 lines per millimeter. There's the laser, that's the diffraction grating, there's the straight through the central maximum, and our first maximum on the other side of it is at an angle of theta degrees, which we know is 15 degrees. So we can work out what the wavelength is. We start with the famous equation, the diffraction grating equation, and that's m lambda equals d sine theta. Now we know we have to rearrange to find out what the wavelength lambda is from that equation, and that becomes lambda equals d sine theta divided by m. So we put in our list of data, we know that the interference pattern we're looking at is the first order one, so m will be equal to 1. The wavelength is what we're trying to find, and we know that sine 15 degrees is going to be 0.259. And therefore we have d, that's the line, the spacing between the slits in the diffraction grating, is equal to the length divided by the number of lines. And we know we've got a length of 1 millimeter per millimeter and 600 lines. So we've got 1 millimeter divided by 600. And that's going to give us 1.67 times 10 to minus 3 millimeters. But we have to change into meters to keep everything all correct, and therefore the slit spacing d is going to be 1.67 times 10 to minus 6 meters. We'll just divide it by 1000. So that's us got all our data. We plug the numbers in and we get the wavelength is equal to 1.67 times 10 to minus 6, that is d, the spacing between the slits, times the sine of the angle 15, that's going to be 0.259, divided by, in this case, the order of interference is going to be 1. And we end up with a wavelength of 4.33 times 10 to minus 7 meters. You can change that into nanometers. That's 433 nanometers. What colour is that? Well, it's a violet colour, so we're using a kind of violet kind of laser.